Hello, this is going to be a quick video on unit laws. So what this really is a bit of dimensional analysis, but I'm going to call it this because it's a really useful way that you can remember and check equations that you write in physics or chemistry or any science really, anything that involves physical quantities that are relevant to our universe. In school they don't really teach this sort of dimensional analysis in schools, and they don't really teach how to deal with units, which I think is a shame because they're so useful. In any calculation it would be advisable to carry the units through, not just the numerical values. Anyway, I'll get into it. So the first one is what I would like to call conservation. So if you have two quantities, A and B, and they're equivalent, so this might be, I don't know, E equals mc squared, so A might be E, B is mc squared, and of course they're equivalent. But the important thing here to note is that the units of A have to equal the units of B if the quantities are the same. I mean, this makes sense. If two physical quantities are equivalent to each other, they're going to have the same unit. So if you deduce that the mass of something is equal to 5 kilograms, then both sides of the equation will have units of mass. It doesn't make sense to equate a mass with a length or something like that. So this is intuitively obvious, but it's useful. And note that just because the units of A equal the units of B doesn't mean the two quantities are the same. So you could have a 2 kilogram mass and a 5 kilogram mass, and clearly the units are the same in both cases, kilograms, or I suppose any other unit. It doesn't have to necessarily be kilograms. It could be pounds or something like that. But clearly the quantities are not the same, so it doesn't work the other way. I'll try and illustrate this with an example. Okay, so here we have the ideal gas equation, which is useful in thermodynamics. It explains the behaviours of simple gases like hydrogen. Relates the pressure P, volume V, with the amount of gas. So N is the number of moles of gas, and mole is just a way of expressing how much gas there is, how many atoms in a sense. R is a constant, the ideal gas constant, and T is the temperature. This is just an equation to illustrate how this works. So both sides of this equation have to have the same units. The units of pressure, of course, are newtons per metre squared. Newtons are, of course, force per area, newtons per metre squared. Volume can be expressed in metres cubed. On the other side, we say that N is the amount of substance, number of moles, so moles here. This is actually a dimensionless quantity, so it doesn't really matter too much if this is omitted, as long as, of course, the other one is omitted, so that both sides of the equation is balanced. But I'm going to put them in to try and be more vigorous. The ideal gas constant happens to have units of joules per Kelvin per mole. That's where this bit comes from. And of course temperature has units of kelvins, or Celsius. The point is, it doesn't really matter which units you use. So in terms of mass, for instance, it doesn't really matter if you use kilograms or pounds, or in terms of length, it doesn't matter if you use metres or feet. As long as you make sure that both sides of the equation are equivalent to each other, it doesn't really matter. But I'm tending to use SI units, that is standard international units, because that's the standard, that's what people use in physics and chemistry. They tend to use these set units, so it makes sense to use these where appropriate, rather than things like feet and pounds and more obscure units, or even Celsius in the case of temperature, because Kelvin is the standard unit. So anyway, I digress. But both sides of these equations are clearly identical. Meters cubed multiplied by meters to the minus 2 is meters, so Newton meters there. The joule, which is the unit of energy, the SI unit of energy, is also equivalent to Newton meters. I think I might have proved that in another video. I don't know, but these two units are identical. And of course, the moles and moles to minus 1, Kelvin to minus 1 cancel. It's important to actually bring up a point here that all of these units can be expressed in terms of a set of base units, and these are things like mass, kilograms, time, seconds, electric current, the ampere. Another one I think is the luminosity, which is I think is expressed in terms of a lumen. I think that's the standard international. Sorry, the candela. The candela is the standard international unit. The candela. Yeah, and there are a few others. And every single unit can be expressed in a set of base units. So this is how I've changed joule into Newton meters, because it can be more basically expressed in this way. Anyway, so this is useful in any calculation check. You need to check that both sides of the equation have the same units. If this is not the case, then clearly something has gone wrong, and this equation can't possibly be true, because the dimensions on both sides are not equivalent. Another way of thinking about it is like trying to equate a two-dimensional object with a three-dimensional object. Say a cube and a square. Clearly they're different things. They're different species almost. And this might be the same as trying to equate a meter squared with a meter cubed. Actually, this is a useful point because it brings us into my next sort of rule: addition and multiplication. If you have a quantity AB, the units of AB can actually be expressed as the units of A times the units of B. And I've actually done that here. I've multiplied the units themselves together. You can do that. If you have a quantity of, say, meters per second, you can multiply the meters and the per seconds together to get meters per second, of course. So you can do that. You can multiply individual units together. That seems to make sense, and you can do that in many different equations. So I suppose the easiest one, which I've just given an example for, is the speed equals distance over time. So speed times time is equal to distance. So speed is in units of meters per second. Time is in units of second. Meters per second times second is meters, which gives you the distance. So so that's something you can do. You can multiply units together like that, and of course you can divide them. So the quantity A over B, the units of A over B, is equal to the units of A divided by the units of B. You can do that. That's fine. The problem comes actually when you try to add and subtract units, which is something you can only do in very specific circumstances. And this comes to the problem I was talking about earlier. It sort of links in with the fact that both sides of the equation have to have the same units, have to be dimensionally equivalent. You can't add units that have different dimensions, just like you can't really add a cube to a square. It doesn't really make any sense. So you can't, if you have a quantity where you've got a sum of a mass and a length, you can't add masses to lengths. The result is meaningless. So it's worth noting that if you have a sum in an equation, you might have a sum. For instance, v equals u plus at, which I've got down here. That's an example of equation with a sum in it. Every part of the sum, every term in the sum has to have the same dimension. Otherwise, it doesn't make any sense. There is an exception to this. You can have, sorry, there isn't. Every term in the sum has to have the same dimension. So in this case, I've got the dimension of A plus the dimension of B, and of course this is equal to the dimension of A and the dimension of B, because of course the units of this is equal to the units of A and the units of B, because both A and B have got the same units. So both are length, both are time, both are masses, whatever. This is how you add and subtract units. You can only do it if the dimensions are the same, and if they are the same, then the result of the addition or subtraction is equal to any given term. It's equal to what all the terms were in originally. So nothing changes under addition and subtraction. I've just made it clear here that the dimension of the units of A is equal to the dimension of the units of B. So they've got the same units, they're basically the same. Okay, so that's almost finished, and that's useful because if you have an equation that has a sum in it, it's always useful to check that the terms have the same dimensions. If they don't, something's probably gone wrong. I think, and it's worth noting that if you do end up with an equation in working out where you're trying to add two terms of different dimensions, something is definitely not right, and you've done something wrong, so you should go back and check. Of course, you can see why this might be useful in memorising equations. If you're trying to add energies to, I don't know, distances or something, then you know that your equation doesn't make any sense in the real world. Okay, so finally, transcendental functions. Actually, you can sort of derive this from the other two. In a sense, it's sort of a combination of these two above. A transcendental function is a function that cannot be expressed as a finite sum of a finite polynomial. So, for instance, the exponential function, or the sine function, something like that, something that isn't algebraic, something that isn't ax plus bx squared plus cx cubed plus dx to the 4 and so on, but something that isn't a finite sum. So what I'll do is I'll have a look at how this affects units for one in particular. So I'm going to choose the exponential function because of the particular property of the exponential function that when you Taylor expand it, you get this very well-known result. E to the a is equal to 1 plus a squared over 2 factorial plus a cubed over 3 factorial and so on. And notice that this sum is infinite. It's an infinite sum. It's transcendental. And this is a very well-known result, which is why I've chosen it. But you could do it for sine, and you'd end up with a similar infinite sum. It won't be as elegant as this, but it's similar. So this is my quantity a, and I've raised a to exponential. I've taken the exponential of a. Sorry. Now these two sides are equivalent, so I'm going to take the units. Look at the units of what happens to the units of both sides. So from the conservation, we have the units of both sides have to be equivalent. So the units of e to the a have to be the same as the units of this sum here. You can see that this isn't really going to work because we've got different dimensions, and we can say that you can't add units that have got different dimensions. It doesn't work. It doesn't make any sense. I've shown here that if you've got a and units of a plus the units of b, they've both got to have the same dimension, but clearly a and a squared don't have the same dimension. Meters and meters squared are not the same. Meters and meters cubed are not the same. These don't work. These have got different dimensions. So the result being that you can't take a transcendental function of a unit, a quantity that has units. For instance, a length, which has a dimension of meters, a unit of meters, sorry, or mass, which has the dimension of unit of kilograms. You can take them, but the interesting result here is that you can, as long as, if a is just a number, so a number might be a ratio of masses, so the ratio of one mass to another mass, that's fine, because of course, since a is a number, the dimension of 1 is equal to the dimension of whatever a is, because they're all just numbers, so that's fine, you can do that. As long as if a is a number, there's no problem at all. The numbers don't have any units associated with them, that's fine. But notice that if a is a physical quantity like a mass, an energy, temperature, a volume, a pressure, all these different quantities, I don't know, a current, voltage, whatever, then you can't take an exponential function of that quantity, because you'll end up with an infinite series with loads of different dimensions that you're adding together. It doesn't make any sense. You can't take the units of 1 plus a squared are undefined. It doesn't have any. You can't do it. So it's often useful in physics to take logarithms of quantities like you might take a log of a mass or a temperature just to make the results easily plottable on a graph. So you'd linearise it like that. But it's worth noting that if you ever do something like this, if you ever try to take a log, which is again a transcendental function, that inside the log you always have to divide by the units that you're using. So for instance, if you're taking the log of a mass, you've got to divide the inside of the parameter of the logarithm by kilograms. Otherwise, you're not taking the log of a number, you're taking the log of a unit, a quantity which has units, which you can't do. So if you take the log of a temperature, you've got to always take the log of the temperature divided by Kelvin. You can't take the log of a temperature directly. You have to take the log of a temperature divided by Kelvin, because of course the temperature has the units of Kelvin, and you're dividing that by Kelvin. The Kelvins cancel out, and you just end up with the numerical value of the temperature. An interesting thing here is also to possibly worry about log rules. So the log of a times b is equal to the log of a plus log of b, and that's fine if we're just dealing with numbers. But if we're dealing with physical quantities, we might come across problems, especially when we're talking about ratios. So the log of a divided by the log of b is equal to the log of a minus the log of b. You might envisage that a and b are masses, so the log of 1 kilogram mass over the log of another few kilogram masses or something. And that's just a number, it's just the ratio between two masses. But if you use log rules, you end up with the log of one mass minus the log of another mass, which is meaningless. You can't take the log of masses. So you've got to be careful when using log rules, that you're always taking logs of numbers and not quantities that have units associated with them. So that's something to bear in mind. And again, this rule is really useful because if you end up with a transcendental function that has a unit as its a quantity with units as its parameter, you know also that you've gone wrong somewhere, and this equation can't work. But people often do take transcendental functions of the numerical value of quantities like temperature, because it does have very useful purposes, especially to linearize data. If you have one way of showing that something obeys a certain rule is by linearizing it, so that you take logs of both sides, and if it follows a straight line, you can see that it obeys certain rules. So people do it, but it's something to bear in mind that you have to make sure that everything inside the parameter is a pure number. Okay.